things, metrics like CPU being used by the user, mem used, GPU usage. All these fields are just standard things that you would see if you were logging your data center usage. More notably, when we, now my approach for this was that I decided that I would use a continuous transformer to predict all the usage. I'm going to go here. The data set has some gap lengths, mostly being of length between 2 to 8, and then there are some that are a bit longer. However, because of the fact that all of the records have a length that is less than or equal to some constant, then we can treat this as something that we can use a transformer for. Specifically, if we set like a sequence length to be that constant being the maximum length of any of these records, then this can be treated as just a sequence-to-sequence problem. The input would be the sequence with missing values, and the output would be the sequence with imputed values. Now, basically, I took inspiration from the original transformer paper by Basit et al. Except instead of applying embeddings at the beginning, at only the beginning stage, I added rotary position embeddings between each decoder and encoder block. This is because there was a paper that said that rotary positional embeddings, when applied each time, lead to better performance, and this lines up with what I had when I was testing out my model. And right here we can see a model comparison of multiple models that I tried. At first I started with the baseline XGB model, which is what was given in our example solution. That performed okay, but then because of the fact that I said this is probably a sequence-to-sequence problem, I decided I would try using a different sequence-to-sequence model. I started by using the DARTS transformer just because that's from the same library that had the DARTS XGB model. However, this didn't produce that great outputs, even with some experimentation on hyperparameters. From there, I decided to implement a custom transformer, basically just using Torch's libraries for that. It performed slightly better, and then the most drastic change I saw was just by applying rotary embeddings before each multi-head attention that I performed. I did perform some other experiments where I tried specifically masking out all the missing data. However, this didn't perform quite as well, and instead I ended up just filling all missing data with the mean, I believe, of the sequence. I also tried training on the previous model. Basically, this was an approach where I tried doing semi-supervised learning, basically, where I train the first iteration of the model on the labeled data that we have, use that to predict on the test data that we don't have labels for, then train a new model on both the original labeled data and the data that has been labeled by our first iteration of the model. While this performed slightly better, it still wasn't that good. And now, after that, I decided to use an encoder-decoder architecture. Originally, I was just using an encoder purely because of the fact that BERT was also just an encoder, and it was also another, it also produced like very powerful embeddings. So I thought an encoder would be all I need. However, it turned out that the decoder helped me have a bit better performance. And then, if I had time, I would have ensembled some of these models and maybe tried more ways to indicate missing values besides simply filling with a specific value, filling with the mean or median, I believe. Okay. Now, as for the other two, I'll start by talking about my approach to inferring user-related preference from conversations with an LLM. For this one, the challenge is pretty simple. Simply build a machine learning model that can detect whether preference matches with a user conversation with an LLM. And the data set simply consists of a human prompt, the LLM response, and a preference and a binary label. The preference being some sort of string about some sort of string like values, values short responses, or detailed step-by-step explanation. Now, each of these conversations is rather long, where the responses vary from pretty short to almost like 2,500 tokens. The prompts are much shorter. About the longest one is pretty long, but most of them fall under 1,000 tokens. Either way, because of the fact that all of these sequences are very long, it would be extremely slow if we were to pass them through an LLM. Normally, token rates are much slower than that, and we have over 1 million tokens in our data set. And that's just my trained data set. And then we have over 500,000 tokens in the test data set. So it would be much too computationally inefficient to pass them through an LLM. As such, we can use a more computationally efficient, if slightly less inaccurate, solution, namely just use embeddings. By comparing vectors in the embedding space, we get a rough approximation of how relevant they are, while at the same time costing us much less compute. There are plenty of embedding models available on like Hugging Face. Most of these have been trained using a lot of data, and they are very small compared to large language models. So anyway, I started by just simply doing a vector similarity approach by just doing like cosine similarity. However, after trying different threshold similarities, this didn't work out that well, achieving only an accuracy of roughly 50%, which is almost no better than random chance. Now, I tried Euclidean distance too, because I thought, oh, maybe a different similarity method would help. However, that didn't work. The final approach that I settled on was simply training a fully connected model on the embeddings, thereby just concatenating the embedding for the prompt, the embedding for the response, the embedding for the label, and training a fully connected model on these. This got a better accuracy of roughly 84%, and that was what I eventually settled on because I was running a bit short of time. If I had more time, I would have liked to at least try using an LLM on this challenge because they should be able to perform at much higher accuracy given their immense natural language understanding. Of course, it would be much slower. Perhaps I would use a quantized model locally or simply just use a provider. And then another thing I could have done was I could have done some hyperparameter tuning or some experimentation with different model architectures. As I mentioned, I simply used a dense fully connected layer, and there could have been much better ways to represent the data. And finally, for the last one, we were supposed to predict serverless function invocation rates. So how I originally understood the challenge was that we were supposed to output the function application at each minute in a day, minutes being 1 through 1440. As such, when I approached the problem originally, I decided I would just use a noise filter in order to get rid of any noise in the input data, remember that, and output that when we were asked to predict function applications for a specific function ID. This works because the function IDs in the test set were guaranteed to be a subset of the function IDs in the train set. However, I have been told that the actual problem was to predict the total number of function applications for a day and not the function applications for each minute. And as such, I go to the if I had time. If I had time, I would have done something similar to that. Basically, if I already have the function applications for each minute, I can simply sum them up and then output that number. Another thing that I could have done is, since I'm only interested in the total number, I could have also combined machine learning with traditional signal processing approaches. If you notice over here, what I did was I simply used a noise filter, such as a Sibinski Golan, I forgot the name, but it's abbreviated SAPGOL. There's also a median filter and low pass filter, and I finally tried like a fast Fourier transform, clip by amplitude, and then inverse fast Fourier transform. I ended up settling on the inverse fast Fourier transform simply because that performed the best out of all of the items, mostly because we operate under the assumption that the noise is going to be basically randomly distributed and have an amplitude that is going to be less than the actual signals comprising our data. Given this assumption, we can just clip by any signal that has less amplitude than a constant. I hand-tuned the constant. And it definitely could have been optimized by like a machine learning model or at least some sort of gradient descent. I am running a bit short on time, so now I will finish up my presentation by handing it over to questions.
All right, thank you. So time for any questions from the audience, and then we'll move on to the question and answers from the judges. Please introduce yourself and ask the question. So this is not live. All right, go ahead and ask the question.
So I'm Hasan from Purdue University. Thank you for your talk about the challenge of frame data user preferences to data engineering these embeddings, and in your future work you kind of indicated how you want to do hyperparameter tuning. In embedding model, did you already incorporate any hyperparameter tuning in terms of parameter tuning or hyperparameters?
Okay, so let me tell you, for that approach, I simply used the embedding model as is, and I trained a model on top of it. The reason for this is because I was running short on time. So I thought like, okay, it doesn't take that much time to just train a fully connected model on top of it, because training the full embedding model would be a lot more computationally expensive, even when using like parameter efficient fine tuning or something like that. That's why I mentioned I would like to do some sort of hyperparameter tuning, like either on the number of units in the fully connected layer, or even like trying to train the embedding model itself and add some parameters there.
All right, other questions from the judges? So we have 3 of the judges here. So go ahead, any of you. Don't let everyone start asking at the same time.
So your first challenge, did you treat all the data as just one sequence, or?
I treated each record as its own sequence. So basically, like I batch everything into sequences of some constant. I think like all of them are less than 512 in length or something. So like I pad them to 512 sequence length sequences, and then I standard like transform return loop on that.
And I think they also have other features in the data, like the host IDs, things like that. Did you find those to be useful in your prediction or in your computation?
I didn't find them to be useful. I did try encoding them, like, and then adding that to the vectors at each stage. Basically, like after each output of the encoder, I would add some sort of representation of the host ID and other features, but I didn't find that to be very useful, so I ended up dropping that.
Can you just put your second challenge again, results preference? No, you had a, that's in the second one, you had your
You're thinking about the third challenge? This one?
Oh, that one. Okay,
Yeah.
yeah, that makes sense.
Yeah, we're supposed to evaluate the model given mean absolute error, mean absolute percentage error, and mean squared error. Those are the three metrics that you see right there. You'll notice like the median filter did rather well in terms of mean average percentage error, but in terms of everything else it does rather poorly, which is why I did end up using just the fast Fourier transform filter.
Yeah, this is the one that you didn't solve for, right?
Yes, I was supposed to output the sum of the minute implications and not just the minute implications.
Kaichun, you have any questions?
So, sir, I came in late, so I missed a little bit in some of the class, but basically is that I don't know, fast Fourier transform. Like, what do you see? Like, is there anything anywhere that it can prove the scale, like the scaling, and what's the capacity for doing this fast Fourier transform in your full project?
I mean, the fast Fourier transform normally has like time complexity of like n million.
Okay, so in your work, what's the size of your data size?
The data sizes are, let's see, we have basically time points from 1 to 1440. So the fast Fourier transform completes in like under a second.
Okay. So can you go up in the previous slides a little bit, like from the start?
Yes. Yeah. So this one is continuous transformer. This one was embedding model. And then this one was noise filter.
Good. So that's the only question I have for you. Who else? I don't have got a big picture. I'm sorry, but yeah, I think that's all for me.
All right. We still have time.
Since you're a second challenge, we are doing the embeddings.
Yeah.
So I think the embeddings are best to represent sort of the content of the text. But there are also things like, let's say, sync step by step, right? So there's this kind of preference of the user. So if the text doesn't appear in the response of the array, how do you, from the simple embedding, we won't be able to find those two things separately. Have you considered like, how to solve those issues?
Sorry, if I understand your question, you're basically saying like there might be cases where the vectors are similar, but the texts don't contain the same words.
Yes.
Right, so for this one, I did just rely purely on the vector representation. I didn't do any like canceling out, mostly because of the fact that a lot of I thought that if they are going to be similar, then it's highly likely that they can, like the two texts can be similar without sharing the same words. Okay.
You said you liked the first problem best.
Yes.
Why?
Mostly because of the fact that I had a lot of opportunity to experiment with that. I had a lot more time on that one before I realized I was supposed to do all three. Yeah.
So really, that was the only reason. Looked like the results there.
All right, let's thank Eliot for a wonderful presentation. And he really was a team of one who came up to the final. So with that, we're going to move on to the next presentation, which is from Purdue University. So even though I'm from Purdue, I have never met these people before. It's a big place. So I think I handled all the conflicts of interest in there. Of course, I'm not judging either. So Hasan, Bilal, and Omar. So take it away, and I'll have that timer running there. So you can take a look at it.
Hello everyone, I am Hasan, and I, along with my teammates Bilal and Omar, are very happy to be here as part of the North American Student Challenge. We are grateful to the IEEE Computer Society, especially the organizing team, for taking this initiative. And let's delve directly into the three challenges. We'll start with challenge number 2, inferring user latent preference from conversation with LLMs. Why? Because people like us like LLMs. So let's first introduce the problem. So the problem indicates that given a human prompt, LLM response, and some potential user preference, we want to infer whether the given user LLM interaction reflects the user's preference. Yeah, I'm not visible. So an example can be that the human prompt is asking to create a storybook, and then the LLM response provides directions on how to create this storybook, whereas this preference, which may be implicit, is that they want it in a step-by-step tutorial style. And does the LLM response reflect that the prompt wanted the step-by-step tutorial? Yes, as we have indicated through this text in bold step-by-step guide. So there is indication in the output would be yes. On the other hand, if the human prompt is such that it is asking to design a login module and the preference is adventure-rich storytelling, the response or the prompt do not indicate such a preference, and the output should be no. Why the problem is problematic, or to us in some sense interesting? First is that we get only a few training samples, just around 2,000 of them, and it is derived from, in fact, a much bigger data set of multifaceted collection from KSTI with over 200,000 samples. So the data set size is pretty small to do any big or real sort of learning. And then the preferences which we want to use for the prediction task, which has been simplified to binary prediction, there are many preferences, over 1,000 of them in just a data set size of 2,000. And in fact, the preferences are not even overlapping between training data and test data, and only around less than 200 preferences are actually overlapping, and the most frequent preferences even are less than 3% or 2%. And for many cases we just get like one preference example, making things complicated for us. So what does this lead us to? An insight that our training data alone is not enough. In fact, through the traditional sort of NLP pipeline, where we have some ML or DL classifier with bag of words or TF-ID or sort of representation, since the information content that we have in our 2,000 training samples is not enough, so we would end up with little better than random accuracy, which is 0.5, even though on training set we may get near perfect accuracy. So how do we address this? So we want something like embeddings. So what we use is these pre-trained embeddings to help classify and understand text through some externally injected world knowledge, because these embeddings coming from, say, LLMs or transformers, they have already been trained on a vast corpus of millions, if not billions, of data. These embedding models convert text inputs into dense semantic-rich vectors. And how we go about it, we take these three input fields on human prompt, LLM response, and preference, get their embeddings, feed these embeddings into a machine learning classifier such as random forest, and make a prediction. We test multiple classification and embedding models and settle on gradient boosting trees with labs or language agnostic bird sentence embeddings. After hyperparameter tuning with k-fold cross validation, this pre-trained approach eventually increases test accuracy to 0.85. So we use these embeddings coming from LLMs, but can't we just use LLMs directly? Because LLM may be all you need. So we end up testing with Llama 3.2 1 billion parameter model, which is already 2 times the parameters than the embedding model. And what we end up with, just 0.6 test accuracy. So this gives us an interesting insight that LLMs right out of the box may not be enough. We need to think about how to improve on how to utilize them, especially the accessible models based on the open source models as well as our compute limitations. So our second step was and this is like a parallel theme of, say, exploring an alternate approach. First was the embedding-based approach. Next we try out LLMs. They do not work very well out of the box. And now we try out how to make the most out of the LLMs. So a quick summary would be, we try to look for improvements in context learning. We provide some training examples to learn the rules in context, and we test with the number of examples to provide whether we just fix some static examples, but since we are not domain experts, we don't know what the best examples are, so we end up dynamically selecting them based on similarity with the current example or just random of them, as well as giving a good mix of negative and positive examples, and we settle on equal number. Secondly, we also try with this chain of thought prompting style, asking it to think step by step, explaining the reasoning, and we get gains around 5% in accuracy. We also experiment with bigger and better models and see that the Llama series of model performs better than the Coin series. And as we increase the model sizes, we also gain advantages on our data set in this context, which can be significant. And bigger and better models generally perform well. So, is LLM obsolete? Well, our conclusion is that almost. So, the LLM-based approach alone performs slightly better than 0.85, which is quite similar to pre-trained embedding approach. So can we combine the two? What we learn is that we can combine the two, but we can do even better, because LLMs are not just providing this output, a binary prediction, and we can combine them in a stacking sort of arrangement. It also helps with explanation for why it is making a prediction. And this explanation is kind of a new sort of data that we are ending with. So we get the best of both worlds. In fact, we get better than best of both worlds. So LLM prediction approach plus pre-trained embedding approach, that gives us something like 90% accuracy, but just combining the predictions. But actually using the LLM response and the explanation and getting their embeddings and using that with the machine learning model, that leads to even better performance. So the key insight is that augmenting ML models with semantically rich representations of text, including predictions, LLM predictions with explanation, leads to extremely high accuracy. Can we do better? Probably yes, because we actually introduce a framework where we can increase performance significantly through using better models, maybe paying for it, and we realize or suspect that just using the Llama 3.1 400 billion parameter model would put us to number one. We already have 94% accuracy, but we can do slightly better. But are real gains even possible, or are we already fitting to annotation noise? So I just leave it here with the illustrative sort of example. So it is a human prompt how to make dill pickles, references straight to the point, and this is the LLM response. This does not go straight to the point, does it? But anyway, the ground truth is yes. The inference is no here, and LLM explanation is quite reasonable, that it is a detailed and includes step-by-step instructions and suggests that user preference is not a straight to the point sort of response. So, which kind of is against the provided ground truth. So, can we do better? Maybe, but we may be already fitting to the annotation noise. And with this, I hand over to my colleague.
Hi, I'm Omar, and because of time being short, I'll go through it quickly. My problem was predict data center missing resource visit data, and basically the problem was we have a given number of CPU or server resources, and for every 2 minutes and some data is missing, so we impute the missing data. First we tried some simplistic techniques like forward filling, backward filling, and rolling mean, and here is next example, and we got 13, 11, and 10 RMSE values. Moving on, we tried some traditional statistical models like ARIMA, and the autoaggressive part of the ARIMA means that past values predict future values, and we found out that 3 to 6 values are good enough for the ARIMA, but we still get an RMSE of 8. Moving on to more newer ML and DL models, we tried LSTM and XGBoost, launch at memory and gradient boosting decision tree. And again, these have a concept of history or lags, and for the best one, we found that XGBoost at 10 history of 4 performed best and gave us an RMSE of 4. So we find 2 insights from this data. One is machine learning models are critical because they perform the best and their use is justified for this task. The second one is I show you that forward fill got an RMC of 13 and backward fill got an RMC of 11. So we show here that there is a higher dependence on the future values for the prediction of current values than on the past values. Combining both of these insights, we firstly reverse the data set. So X is the data we want to impute, and then we use XG rules for a lag of 4 to predict the current value at X, and we achieve an RMSE value of 2.5 using this approach.
Okay, so the third problem is to predict the invocation rates for the functions using historical data, but we have 3 main objectives that our solution should be and effective with the reduced or error rates, and it satisfies efficiency that the training time should be within the 1 read rate of 1 hour, and then it should be able to handle if we introduce noise into the data. So let's look at the data first. We saw that the data that we were given is highly sparse. 85% of the values are 0. What happens is that it hurts our efficiency and our effectiveness because it's not relevant and it's huge amount of data. How can we do? What should we do about it? We just we pre-process the data and convert this data to the sparse metric so that the sparsity can be removed or it can be lowered. And then we also do the feature selection using various thresholds so that our effectiveness, so we can increase our effectiveness, so that our errors are reduced. We used random forest for our prediction as a prediction model. That's tree-based ensemble method. So there are 2 main parameters that we tweak: the number of estimators and the max depth. So max depth helps us with the accuracy, and the estimator helps us to reduce the training time. So if we evaluate our model with respect to the dummy predictor values that were given, that assumes that every prediction value is a 10. And then for the very basic initial data, it takes 1 minute, and the error rates are 0.84 because it's almost similar to the dummy prediction values as a value of 10. Why the MAVE was high? Can we do better? Yes. As you can see from here, we started increasing the depth parameter. As we increase the depth, our error rate goes down, but our training time increases. But as we decrease the number of estimators, our average error is almost the same, but our training time has been reduced a lot. So what happens? But this is all good. But right, what happens if you add noise? The error rate goes up from 0.17 to 5.8 if we add just a noise of 10%. So what do we do? Our approach is to handle this kind of situation is to add a noise in our training data. We add a noise of 5%, and we use 25% of that data, and add a noise of 10%, use 50% of that data, and add a noise of 25% into the test, and then use the result. With this result, we get around 30% better gains as compared to the original data without the noise. So thank you very much.
All right, so let's see if there are questions for Bilal, Hasan, and Omar. Firstly, any questions from the audience?
Hey, great presentation. I just had a quick question. With the methodology in problem, the second problem we discussed, in the backwards fill, in a production environment where you don't have access to future values, would you do you have any ideas on how you could still leverage that I guess like backwards? You said you had an insight, right, and reverse the data, right? So yeah, do you have like any thoughts on how you could potentially still leverage that?
Go ahead and introduce yourself.
Sure. Yeah, my name's Daniel, and I'm a student at Rice University.
So the problem wasn't time series forecasting, it was data imputation. So because of that certain aspect, we already have all of the data set and some values are missing. So we treated it as parts of it as time series forecasting when we reversed it, but we already have all of the data, so we can get away with having all of the data set. And even as Eliot tried in his first attempt, you can just give all of the data to the LLM as well.
I understand. Okay, thank you.
Any other question from the audience? All right, we'll open it up to the judges now, so that Huang doesn't have to go first every time. We can randomize the order. Does anybody have a question?
For this slide, is there a kind of logic that you pick the capacity that you're going to test? Is there some kind of capacity you're picking from the toolboxes? Consider certain kind of, by picking this method, what kind of the logic you're following? Why not? Why this maximum and I mean, not other kind of sequential-based sequential models?
Thank you for this question. So, in benefit of time and for clarity, we just included like some methods. A high level insight was to try 3 types of method. One is just like basic arithmetic operation like rolling mean, backward fill, forward fill. Another was this classic time series model like ARIMA, SARIMA, exponential smoothing. We also explored that, and like the third is these machine learning sort of models, LSTM, XGBoost, random forest, even transformer from the DARTS model. So the insights that we got on a higher level was that say these groups of models perform similarly well. So ARIMA versus SARIMA, we did not get gains, and in fact looking at the data, we know that our data does not have any seasonality. So we did try that, and we get generally consistent insights about how a particular group of models perform, and then based on the hyperparameter tuning and so on, we just decided to stick with XGBoost.
All right, with Rachel's question done, who wants to go next? Alia.
So similar to the question that I asked to Eliot earlier, so in the first challenge, have you found any other features to be useful than the machine IDs? So the reason why I ask it is that even though you said the challenge that the machines, like you don't have the prior knowledge of what machines are similar to each other, but from the data, even though some data points are missing, maybe you can compare, right? Those 2 machines are probably similar around this time, and then if one of the sequence has the data while the other doesn't, maybe you can use that to do the interpretations instead of just relying on the information from just a single sequence. Have you considered that?
Perfect. That's an excellent question. So we did consider that, and we did see some, say, trends in the data which indicate that they should be quite effective, but I think it may be implementation shortcoming on our end based on the limited exploration that we, based on say our own testing, we could not get this additional information to work better than what the implementation that we just presented. So yeah, but I think there is room for incorporating this information, and based on our data exploration, we suspect that getting it to work can improve our results further.
I would like to add that the model, all of the methods we tried was univariate, so only the sequence like CPU usage was only dependent on CPU usage. So if we were to add host ID and the CPU job ID, we probably would have liked to use the transformer model for that. And for the shortage of time, we didn't really explore the transformer model. We only used the DARTS transform library, and from the library implementation itself, it says that the implementation is very simplistic and not very complex. It's not according to the latest architectures of the transformer. So one thing that we should have done was explore the transformer models more, but for the short of time we could not.
So the third challenge, what's the intuition behind the random forest method that you choose? And also what's the intuition behind like choosing like the different percentages you choose for
Sure. So the choice of specifically taking random forest, this is not as critical, but say one motivation was going for decision trees, and then an ensemble model for decision tree and random forest XGBoost. They work similarly well. XGBoost we from to take a higher runtime. That's why we stuck with random forest. The advantages of random forest was a decision tree based ensembles is one, it offers a bit of interpretability, but beyond that, through this decision tree and rule-based structure, we found that say increasing the decision rule complexity and controlling it through a certain parameter, which is max depth here, that is relatively easy. And as seen in this table, the max depth led to significant gains. And this isn't that say all the branches are extremely deep, but occasionally there are certain decision rules that need to be particularly complex and where we need to go particularly deep. That's where decision trees are helpful, and then we just wanted to go with the ensemble model for decision trees that leads to higher performance. Secondly,
So the reason is that 5% if you reduce 5%, it's quite close to your original data, not too much variance. So the data that you would have seen in the original data would also be there in the 5%. Most of it would be in the 5% noise too. So you don't, if you add all of it, like 100% of the data with the 5% added noise, you would be increasing your training data by two, like you are doubling your training data. So you're essentially increasing your training time, basically. So we try to reduce your training time as well as keeping your accuracy or error bars low. So that's the equation that the 5% as the less the noise is, it's close to original data, so you don't need to train it again. But as you increase the noise, you need more samples basically. So that's why we increase our 50% 100%, so that we have more data for instance. We can double.
Thank you.
All right. So let's thank the team from Purdue once again. And finally, we have the team from Rice University. And Daniel and Jonathan are here to represent the team.
Alrighty, my name is Daniel Leeds. I'm a master's student at Rice University.
My name is Jonathan Mack. I'm a senior at Rice University.
And we also have a third teammate, Harrison, another master's student at Rice University, however, he's unable to attend. So, presenting our work on imputing the missing usage data for a supercomputer, we first want to motivate the problem. So the usage characteristics that or features that we have include CPU usage, memory consumption, GPU activity, and data transfer rates. These features are very important for cloud providers like Amazon AWS, Google Cloud, Microsoft Azure, and properly giving out tasks that as they come into their cloud platforms, distributed tasks on their compute racks. Similarly with supercomputers, such as Al Capitan, this is the most powerful supercomputer right now. We really want to minimize the downtime of any of the compute of these computers. So the data that we were given had a few challenges, including that the missing data was showed up at inconsistent time intervals, and also you have distinct simultaneous time series. So you have multiple devices or hosts, and they will each be running their jobs at the same time. So we did interpret this as a time series forecast in the for production environment. Again, like cloud providers being able to properly distribute those tasks. So given that this data is coming in at intervals, we came up with a few potential approaches, like statistical methods, that's basic moving average, moving median, some machine learning methods like ARMA or RIMA, and then more advanced deep learning approaches like LSTM and transformers, given their recent success in a variety of domains. And this equation just gives a general outline of basic time series that evaluate time step t and depend on some parameterized combination of previous time steps plus some random noise. So further diving into the potential approaches, there are univariate approaches like moving average and moving median, as well as autoregressive based approaches. You also have multivariate approaches, specifically specifically deep learning approaches like recurrent neural networks or extensions of those in forms of long short-term memory models, as well as transformer-based approaches. So before getting into the specific model details, we had to go through some data exploration. So we wanted to observe the distributions of these features to one, and these two plots give a good idea of the two feature distributions that we observed. So these are flattened representations of the entire data set, and you can see in the case of block, we have pretty consistent values over time with some sporadic extreme outliers. This compares to CPU user, where we have some periods of stability followed by great periods of variance. However, those periods of variance are in pretty consistent intervals over time. We also explored the autocorrelation between features, which gives an idea of the dependency of previous time steps on a current time step for a given value. In the case for a block, again, these are representing all features. Block shows a pretty flat trend, which is indicative of a lacking of dependency on previous time steps, whereas CPU user has this exponentially decaying plot, which does in fact indicate some trend or seasonality to the data. So in addition to the data exploration, we needed to properly format our data to feed into our models. So given that we have multiple different hosts, again devices, and each one of those hosts will be running their own jobs, we were able to utilize IBM's time series foundation model software package to pre-process our data set in a flow demonstrated here. So given two different hosts, we want to take these non-contiguous time series and create a continuous time series. So for a given host will take the first job, and this eliminates the necessity of relying on timestamps. So it's the first job, and basically concatenate job 2 after that, have a direct continuous following time series, job 3, and would repeat the same process for another device, another host. So the first model that we explored is patch TST. So this is a research model developed by IBM and Princeton, and this takes on two key adaptations from a basic transformer. One is the ability for it to take our feature values and transform them, which we'll discuss later on, into their own time series, univariate time series, and even still leveraging attention, it's able to treat each one of these univariate time series independently and compute predictions for that in parallel. Kind of getting into more details of this patching, you can think of it as convolution, except there's no convolutional kernel actually being applied. But for a given time series, so for a given feature, one of these univariate time series, we basically are using a sliding window to take a chunk out, and this chunk will be then transposed and projected into a higher dimension. And there's also positional encoding to give relative position of where that chunk of the time series fits in the end-to-end process. And to give you an idea of why transformers, the real motivation is attention. You can use attention to give the relative importance of previous time steps to current time step. So in attention, you have key queries and values, which are all unique linear versions of the same input. So for these input time series, you'll basically compute the dot product similarity between them. This will give you and then you use softmax to give you the relative similarity of these time series. And that's relative importance is used as a weighting to the value vector, which again is just a linear transformation within our original time series. And transformers add one layer of sophistication on this with multi-headed attention, which just basically looks at this original query key and value space, and you can look at subspaces in that, basically allowing the model to capture more complex relationships within this time series.
So in addition to our patch TST model, we also wanted to go try out a more traditional time series imputation model, namely LSTMs or long-term short-term memory. So LSTMs are a type of recurrent neural networks, which is specifically designed to learn long-term dependencies in sequential data. So they primarily do this through their memory cells, which have 3 different gates: the forget gate, the input gate, and the output gate. So a traditional problem with RNNs is that after some point they stop learning new information. So through the memory cells, we're able to forget and input we're able to input and forget various information, allowing the model to learn long-term dependencies, this in spite of how much data we feed it. So this makes it particularly suited to learning time series data. Unfortunately, LSTMs also have a couple weaknesses, namely that they take a long time to train, and they also are very sensitive to hyperparameters and random weights. As a result, we decided to try and experiment with a hybrid model by combining LSTMs with LightGBM. So LightGBM is a highly efficient implementation of a gradient boosting decision tree, and accomplishes this by creating decision trees and creating new leaves, new nodes through the leaf-wise process. In which case it explores and creates new leaves for whichever leaf has the largest loss. This allows GBM to convert very quickly, leading to fast and efficient imputation results. So we can see our LSTM hybrid model pipeline sort of looks like this, where first we process the data in the process that we discussed before. Then we send that processed data into the LSTM for training. Then we get the features and send that to LightGBM for training. And finally, we have our model for time series data imputation. So here we can see the performance of our model. We implemented 3 different models. We have our PatchDST, the LSTM hybrid, as well as a basic naive RMSE, which essentially just found the average for every single host and for every single host in every single category and imputed it and filled the missing values with the set average. So as you can see, while PatchDST did perform well, LSTM hybrid really just outpaced the competition, outpacing both PatchDST and naive RMSE, significantly improving their performance on GPU usage, memory use, and memory use minus disk cache. We also see this performance continue with the other 3 categories, namely block, CPU user, and NFS, with once again a PLSTM hybrid outperforming all 3 models, the other 2 models. So in our LSTM hybrid model, our LSTM dramatically outperformed PatchDST. Our hybrid model had an average RMSE of 3.84 compared to PatchDST, which had an average RMSE of 26.49. We think that this is primarily because LSTMs were designed for these sorts of time series imputation problems, and because of the memory cells and the forget gates, we were able to capture hidden dependencies inside the data, as well as because of the hybrid model, we were able to reduce inter-model complexity. As for future work, in the future, ideally, we'd like to, given the success of our LightGBM hybrid approach, we would like to experiment with trying out a PatchDST LightGBM hybrid approach and see how that works. In addition to that, we would also ideally like to train both models with more data. LSTMs and in particular PatchDSTs really thrive with the PatchDST transform model really thrives with increased data, and we feel like with more data, more trained data, we would be able to dramatically improve the performance of both models. Next, we would like to apply search algorithms and agent optimization techniques to search for hyperparameter space. This is because both models are significantly significantly benefit from hyperparameter tuning, and unfortunately we weren't able to do that much hyperparameter tuning, so we believe with by implementing these techniques, we will be able to improve the results of our models. And finally, we would like to experiment with how our models perform on various other time series data, not with just this specific data set, but with other data sets, and see how they perform, to see how well they generalize this to other problems. Thank you very much for listening. We have created 2 novel approaches in creating in this problem of time series imputation versus PatchDST, which performed well, and we also have the LSTM hybrid approach, which performed very well. All our code is open source, and all our data is free to use. Just scan the QR code, you'll see a link to our GitHub. We'd like to thank you guys for listening, and thank you very much.
All right, let's give it up for Daniel and John. Questions from the audience? Okay.
You mentioned that you had combined concatenated all the records for any specific host. Does this introduce dependencies between different time series? And if so, did you experiment with not concatenating?
Yeah, so that data process that is very specific for training. And again, if this model was being used in a production environment, you would have multiple copies of this model and use it as needed for a given host or device. But as far as dependencies go, the goal is for training, you need the let me think of actually I don't think it certainly wouldn't create dependencies between devices. It potentially could create problems in around the concatenation time steps. However, the model should be able to essentially learn that trend and whatever characteristics you see towards the end of a scheduled job, that is learned as part of the seasonality, the trend in the data, so that you can accurately learn that the preceding time steps are likely to be representative of early jobs, whatever that those characteristics look like.
All right, we'll move on to questions from the judges.
Can you put up your graph again? I did like your graph.
Yeah,
But
absolutely.
it doesn't look like the patch test did better than your, what was the first one, the random approach?
Yeah. So patch DST
Or not
definitely,
even?
yeah. So patch DST definitely,
Did worse.
Yeah, it definitely struggled. I think this really exemplifies how sensitive transformers can be to training and hyperparameters. The hyperparameter space for patch DST is even more complex than basic transformers, and I think there's quite a bit of work that can be done to optimize those parameters, and I think another aspect of it may just be the complexity. So we only have six feature values. So in order to leverage the transformer, we had to try and project these six feature values into a larger vector space, because using attention with only six features or six embedding size of six really wouldn't be a good use for attention. Also, the attention mechanism is particularly good at long-term dependencies. So it may just be in the case of this time series data that whatever the underlying trend is, the relationships are more short-lived, and that's likely why LSTM does perform quite well with the memory cells being able to specifically remember for just weighted transformations, shorter relationships. Patch DST definitely is great.
Actually.
Thank you for the presentation. So my question is going to be related to your future work. I think it's really good data you summarized some of your visions in the future of this work. So specifically for the third one, you mentioned that you want to do some parameter search to fine tune and get a better setting. But my question is related to the patch TST is transformer related tuning. So it's not just about hyperparameters as numbers. You may have to add in some different layers with different node, batch,
absolutely.
layer norms. So how do you decide use based on optimization and search algorithms to deal with those kind of tuning?
Yeah, absolutely. So with the I think hyperparameter space here, absolutely. We could I guess call it a model parameter. But yes, like number of attention blocks and various embedding dimensions, projection dimensionality. Absolutely, these are all critical. And so obviously trying to run a greedy search on all these different combinations would be not very feasible, and that's why something like Bayesian optimization, where you essentially trying to make intelligent decisions after observing a subset of evaluation. So like you pick some subset of possible hyperparameter combinations. We evaluate the results after a limited number of epochs to see how the weights are converging, and based on that, you can make adjustments to the hyperparameters, if you'd like to refer to them as model parameters. But yeah, absolutely, potential block and other projection dimension and dimensionality. All these would be critical. Yeah. It's very sensitive. Yeah, transformers are And this I think it really exemplifies, especially applying a transformer, right? Like I said, starting with just 6 features. This may be an example of why complex deep learning models aren't always necessarily the best. Just to throw at any given problem.
All right, and we have a question from Huang.
So I think when we're dealing with time series, sometimes we will create our own features on the original models. Have you tried that?
Yeah, great question. We did not experiment. We actually, especially if we were to go with something like ARMA or RIMA or more basic ML or statistical methods, I think feature engineering would have been much more important, or even just transforming some of these values, applying certain types of linear-based or even non-linear transformations. However, when we decided to go with these more complex deep learning models, we didn't find that feature engineering would provide some great benefit.
Thank you.
All right, with that, let's thank Daniel and Jonathan once again. And for the judges and for the finalists, if you would now congregate at the front, we have to take our obligatory picture.